Hey there, hope everyone's doing good. This video is going to be binary search in Python, so a very fast searching algorithm across a sorted list. Sources for this you can check in the description of the video. They should be down there. This slideshow is a public Google Drive link, so you should see it down there. The code is going to be right here. You go down here, project full stack, GitHub, we have searching algorithms, and then a binary search. And there's the one I have for this, an iterative implementation of the binary search method. So you can go down here, you can look about it, and you can click it raw and copy and paste it in and play around with it all you want. Let's see here, back here, Wikipedia. I do reference Wikipedia for the definition, kind of what a binary search is. So the link is there for the binary search algorithm. And then BigO cheat sheet, absolutely love this. I'm a huge supporter of them. I don't get any kickbacks or anything by pushing them. I just really love their website there. I use it a lot. All right, so what is binary search? This is our Wikipedia definition. In computer science, binary search, also known as half interval search, logarithmic search, or binary chop, is a search algorithm that finds the position of a target value within a sorted array. Okay, it has to be sorted. If our array or our list is not sorted, you cannot use a binary search. It works by a divide and conquer strategy that will divide a list by half after each check. So each time we're going to basically take our whole list and we're going to make one comparison. And then we're going to say, based on what we're searching for, if it's less than or greater than, we'll do some stuff, but we're dividing by half. And then on the second iteration, I've divided by half again, and half and half and half. So it works by reducing our search space by half every single computation, which means we can take extremely big search spaces, extremely big lists, and search them in a very fast way. All right, it's an algorithm that, given a sorted list, again, can search a list and at most log base 2 of n plus 1 comparisons. So what does this really mean? That's log base 2 of n. That's basically saying divide by half every single time. And this is what it comes out to be. So if I have a list of 64 elements, I can search the list in at most, so I'm talking worst case situation here, log base 2 of 64 plus 1, which comes out to be 6 plus 1, or 7 steps. So given a 64 element list, I can tell you within 7 comparisons if something is in there. 32 elements, now we're log base 2 of 32 plus 1, which is going to boil down to 5 plus 1 or 6 steps. If I have 16 elements in my list, I can do it in 5 steps. 8 elements, I can do it in 4. 4 elements, I can do it in 3. 2 elements, I can do it in 2 steps. So hopefully you can already kind of look at this and be like, this is much faster than linear search, right? If I was going to do a linear search across 64 elements, I would have to start at, index 0, check it, go to index 1, check it, go to index 2, check it, go to index 3, check it, so on and so forth until the end of the list. So my worst case for searching a list in linear search of 64 elements is 64 steps, but I can do that same search in 7 steps in a binary search. So that's already much faster. And it gets even better on a grand scale. By a grand scale, what I did was I went and I looked up how many stars are in the Milky Way galaxy. And there's an estimation between like 100 billion to 400 billion stars. So I said, all right, if I have a 100 billion a list with 100 billion elements in it, how fast can I search that using binary search? So we take log base 2 of 100 billion, we add 1, come out to be 37 plus 1 or 38. Think about that. You can give me a list that's 100 billion elements and tell me, does this number exist in that list? And I can do 38 comparisons and find that out. Across 100 billion elements, I only need to do something 38 times to tell you if that thing's in the list or not. That's crazy in my mind. Okay, linear search, what's our worst case here? 100 billion, because I'd have to do an exhaustive search. I'd have to traverse a whole list. So linear search on 100 billion elements, worst case is 100 billion. Binary search, worst case is 38. That is massively different. That's great. So here's what our BigO is. If you're not familiar with BigO, that's fine. You don't need it for this algorithm. Most people that are looking up searching algorithms are in some type of data structures and algorithms class, so they probably already have a little bit exposure to BigO. All this is saying is that your worst and average case, this 38 step thing we talked about up here, is log base 2 of n. Basically what we have here, log base 2 of n plus 1. Our best case, being that we find it on our very first comparison, is 1. Very fast algorithm. Okay, here's the BigO cheat sheet. Again, go to their website. They even got a poster there. Buy it, hang it up on your wall. I love it. I don't get any kickbacks or anything from supporting these guys. I just love their website. Here's our O to the log base 2 of n there. So this kind of just shows you a chart of our different algorithms, how efficient they are, and how they rank. So all the stuff up here in the red is bad, or horrible, I should say. That's what that says, horrible. Orange is bad. Yellow is fair, green is good, and bright green is excellent. And that log base 2 of n is basically down there in that good/excellent area. I think it's an excellent one myself. So it's very, very fast. Okay, here's the pseudo code. This is going to be confusing until you actually see the kind of next slides, which have some animations that should hopefully make it a little bit easier. So stick with me here. But all right, remember, we have to have a sorted list. This algorithm does not work with an unsorted list. Okay, so given the sorted list, searching for a given number, I need to set some left limit equal to 0, because that's basically going to initialize the left side of our list, being like, hey, this is the left side, the left limit of our search space. I'm going to set a variable right limit that's going to equal the last index in the list. Right, so left limit points at the first index, or 0, and then right limit points at the last index in the list. So basically, we're going to search across our whole list from the get-go. We're going to initialize a variable called middle. Right now, we're going to set it to 0. We're going to mess with that in a second. If you've seen other examples of this, a lot of times people will use like min and max for these left and right limits. That's fine. I just wanted to, I thought just kind of spelling it left limit and right limit would make it a little bit easier conceptually to understand, but you can name these whatever the heck you want. All right, so while left limit is less than right limit, okay, we get the average of the left limit and the right limit rounded down. So this is basically going to give me the middle index. All of this step is really doing is saying basically between the left limit and the right limit, where's the middle? We have to find the middle, because that's how this algorithm works. We're going to take our whole search space, we're going to look at the middle of it, do a check, and then move our search space left or right based on that. So I have to find the middle. The way you find the middle is you take the left limit, you add the right limit, and then you divide by 2 and round it down. And you'll see that in a second. Once we have the middle index, that's key, that we have the middle index, now we can say, is whatever that index, that middle index, is that what we're searching for? If it is, perfect, we found it, return that index. If it's not, you need to do a comparison, basically saying, is it less than or greater than? So if the value of that middle index is less than what we are searching for, which means the key we are searching for is greater than whatever is at that middle index, we know, because it's a sorted list, that the key we're looking for should exist to the right side of the list, right? That's why it has to be sorted, because we're going to look at that, the value at that middle element, the value at that middle index, and we're going to move our search space based on if we're greater than or less than that. If the value of the middle index is less than what we are searching for, move the right limit variable to be the middle index -1. And yeah, that's a little repeat there, but if the value matches, return the middle index. Otherwise, if we get all the way to the end of it and left limit becomes greater than right limit, that means we're done searching. The key does not exist, so just return false, or case what I'll be doing is returning -1. So let's look at what this actually looks like. All right, this is going to be the value we want exists in the list. So we're actually going to find the value in the list. Then we'll do an example where it doesn't exist. All right, so here I have a list of, what do we got? We got 0, well, we should say we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 elements. So what we need to do is set our left limit to 0, right? Because that's going to point to the 0 index, or the start of the list. We're going to take our right index variable and set it to be the last element in the list, last index, which in this case, this is index 13. And we need to find the middle index. So to find the middle index, we do left index plus right index divided by 2. Then round down. So in this case, I'm taking the left index, which is 0. I'm taking the right index, which is 13. I'm dividing that by 2, which gives me 6.5. I need a whole integer, so we just round it down to 6. Okay? So basically, if I look somewhere in this list and I take the left limit, the right limit, divided by 2, round it down, it's telling me the middle is right here at index 6. Okay, so 6 is my middle index variable. Okay, I then compare the value that I find at, let me back up here. I then compare the value that I find at this middle index, 73. I compare that against what I'm searching for, 42. Okay, 42 is less than 73. So because this is a sorted list, I know that 42 must exist to the left side of that number, right? So what we're going to do is we're going to take this right pointer and we're going to move it to the middle index, -1, which is going to put it right here at 61. Makes sense, right? Because we already searched 73. We know that didn't equal 2. We know it's less than, so we know it's not 73, so we can literally chop off this whole side of the list over here. Right? We can chop off this whole side of the list and then move our right index here, and now we have basically eliminated half of our search space. This is what this next slide does. It basically says the same thing, but you can see now how I've moved that right index all the way over here, and it now points to index 5. Okay, so we looked at what was at the middle index. It was less than, so I took the right index and moved it to the middle index -1. A common mistake people have is to move it right here to the middle index. You don't want to do that. You want to move it to the middle index -1, because again, we just checked the middle index. So I no longer need to even include that in my search space. Next up, we do the same thing with the middle. Okay? All we do is we take our left index, 0, plus our right index, 5. We divide that by 2, which gives us 2.5. We ran that down to 2, and that says, hey, 2 is the middle index between these two elements, between these two indexes. So we repeat the process again. We check what's at the middle index. Okay, we check what's in the middle index. We said we found 32 at the middle index. What are we searching for? 42. Well, I know 42 is greater than 37. So I can remove all of these over there because I know it's greater than. We've already removed from what, 73 up? Like that. So now we're left with these three. And I say, okay, since it's greater than, I take my left limit, which used to be here at 0. I move it to the middle index, which is 2. I move it to the middle index, which is 2, plus 1. Because again, beginner mistake is to put your left limit here. You don't need to put it there. You actually need to move it 1 pass, because we've already checked here at the 37, the 2 index, so we don't care about that anymore. Get rid of all these, and let's go to the next slide. Okay, we do our calculation here to figure out the middle. So we say given the left and right limit, so I take 3, index 3 plus index 5, right, which gives me 3 plus 5 is 8. I divide that by 2, I get 4. Round it down. In this case, it's already rounded down, so it doesn't matter. But that gives me a middle index of 4. We do this again. Is 4. Is the value we found at the index 4 equal to, greater than, or less than 42? In this case, the value is greater than, so we know that we need to move left. So we've eliminated 37 to the left previously, 73 to the right previously. Now we know 42 is less than where we are at this middle pointer, so I'm going to eliminate that. which means I need to drag this right limit over here to be my middle limit, -1. And in this case, they're still the same. Left limit and right limit are exactly the same. They're both 3, which is okay. We then compare the value found at 53, what we were searching for 42, because the value at the middle index 53 is greater than what we were searching for, then we know our search value should be to the left of that number, which is perfect. We take the right limit 4, set it equal to the left limit -1. That's all that's same. Then we're going to go here and we're going to move our middle pointer again. 3 is our middle index. We're going to do our comparison. And in this case, we say, hey, 42 matches what I'm searching for. That's awesome. Return that middle index or return 3. So that's how this works. Recap real fast. Just go back here. Left limit starts at the beginning of the list. Right limit starts at the last index of the list. Middle is in between them. Okay. You do a comparison. In this case, it was less than, so we moved our right limit 1 past our middle limit, or our middle -1. Recalculate our middle. 37. It's what we're looking for is greater than 37, so I need to move my left limit here to be middle +1 to put it right here. Figure out what our middle is again. It's 53. 53 is greater than 42, so I need to move my right limit to be my middle -1, which puts it right there. I need to recalculate my middle. This case, they're exactly the same. All 3 pointers point to the same index, which is fine. Recalculate that and do a comparison. 42 is what I'm looking for, so 42 is returned. Or excuse me, the index is returned. 3, the index is returned, not the value. All right, what if the value does not exist in the list? Okay, in this case, it's the same exact list. We're basically going to do the same exact process. In this case, we're looking for 49, which doesn't exist, right? Sorted list, we know it would be between 42 and 53. So it should be somewhere over here, but it doesn't exist in this list. Okay, again, starting situation here, left limit is set to 0, or the start of our list. Right limit is set to 13, the last index of our list. We calculate our middle, which in this case comes out to be the index 6. Do a comparison. 49 is less than 73, so we move our right limit over 1 past the middle. Recalculate our middle, which is now 2. Do a comparison. Is 37 is less than 49, so I need to move my left limit 1 past middle. Recalculate my middle. Okay. Do a comparison. 53 is greater than 49, so I need to move my right limit 1 past middle. Recalculate my middle. Do a comparison. 42 is less than 49, so I take my left limit and I move it 1 past the middle. And in this case, we're done. Why are we done? Because we reach our exit condition where our left limit is greater than our right limit. Right? We've already searched the 53. We don't need to search it again. We know that 49 does not exist in this list. I'll go back up to the pseudocode all the way back here. And remember right here, while left limit is less than right limit. So this is our exit condition. So if left limit becomes greater than right limit and we haven't matched a number, we return false or -1. Here is the code all the way up here. There's a GitHub source, so you can look at that. I'll bring up PyCharm here. I'm not going to step through it. I think it's somewhat self-explanatory. Let me put all my comments back in here that I deleted just to get a good shot of that video. Okay, and let's run this. And let's just see what happens. Okay, I searched for 42 in that list right there. Same exact one I had in the slideshow there. I found 42 at index 3. 0, 1, 2, 3. Perfect. Test 2. search for 49 in that same exact list in the slideshow there. -1, because it doesn't exist. Remember, it should have been between 42 to 53 because we know this is a sorted list. So at some point our left limit became greater than our right limit and we exited. Okay. Then I did some more search cases just to check my algorithm. I searched for it in an empty list. Came out with -1, which is good. What I did not want to see here is an error. I didn't want to, say my algorithm works for stuff that lists that have elements, but for some reason you pass in an empty list and it's broken. So it works for an empty list, returns -1. Then I tried it against a list with only one element in there. So in this case, it's in there 49. We found it at index 0, which is perfect because that's exactly where 49 is. And then again, a one element list with a number that doesn't exist in there, and I get -1. So all the testing should work here. I'll walk through the algorithm real fast. So I define a new function called binary search. Again, call it whatever you want. It needs two inputs, two parameters here. One, it needs some type of sorted list, right? So we're going to pass the list in, and then it needs to know what it needs to search for. So we're going to pass our search key in there. Okay. Here we set our left limit to 0. Remember, that's supposed to be to the left side, or the 0 index in the list we're going to search. We took our right limit and we set it to be basically the last index in the list. This is how you can find it in Python. You take the length of the list and subtract 1 from it, and that's going to give you the last index in Python. Then we set our middle index to 0, and we have a good starting state. So then I say, while left limit is less than or equal to right limit. Okay. Find the middle index. So we take our middle index, we take our left limit, we add the right limit, we divide that by 2 and round it down. This is floor division right here. So if you just do a single one, you're going to get a float back. But if you do 2 of these, you're basically going to get a floor division. So this does the dividing by 2 and rounding down. So we have our middle. Then all we do is check that list, right? Check the index of the middle that we found. Say, is it less than the search key? If it's less than the search key, we know that we need to move that left limit up. We need to move the left limit to the middle index plus 1. Otherwise, if what we find at that middle index is greater than what we're searching for, that means our value should live to the left side of that index, of that middle index. So we're going to take our right limit and move that 1 from the middle index. So middle index minus 1. Otherwise, if it's not greater than, or excuse me, if it's not less than and it's not greater than, it has to be equal, right? So we just return the middle index. That means we found a match, so return the middle index. Otherwise, if we get all the way down here, basically we're out of this while loop, so left limit has became greater than right limit. We know we're done searching. That's the end of our algorithm, so we just return -1. And here's my test cases here. Again, you can look up this code in the GitHub there, so I'm not going to, just kind of leave it up and let you copy it all down. You're free to just go to GitHub and check it out there. But here's all my different test cases, nothing fancy. But as you can see, it's a fairly simple concept, fairly simple algorithm, and it's extremely fast. So, all right. That's it. That's all I got for this video. Hopefully you got something out of it. If you liked it, let me know. If you didn't like it, let me know.